let's take a look at some of the examples on Chapter 6. So example 6.1, go ahead and pause the video, read the problem carefully, write down things that the problem is giving to you, the information that you have, and then let's solve it together. Okay, so we have a 50-gram salt shaker. So M is 50 grams, okay, and you slide the 50-gram salt shaker in the direction giving in the initial speed of 1.15 meters per second. So initial speed of 1.15 meters per second. If the shaker comes to rest with constant acceleration, okay, in 0.84 meters, so the displacement here is 0.84. That's what it is. All right. With a constant acceleration, doesn't say how much it is, but we know it's constant. What is the coefficient of kinetic friction between the shaker and the table? So when you're looking at this, you have a salt shaker, and then which I'm just gonna say if it is a box, doesn't matter. So I have a box, I have W, which is mg, down, I have N up, and then I have friction, F of K, and this is the direction of motion. So this is where it's going to. So the friction is always in the opposite direction. We always know that the forces along the y direction should cancel out. So we know that N is always mg. We know that. Along the x direction, I will write Newton's second law. Okay, f of x equals ma. F of x is the only force acting on the y direction is friction, so which is f of k, and it's along the negative direction, so I have to have a negative here. Okay, so a negative sign equals ma. Negative f of k is mu k times n equals ma, and so we have negative mu k. We know what n is, we know it from the y direction, so I'm just going to substitute that, which is mg equals ma. At this point, you can easily get rid of m and cancel it out from both sides. So this m and this m will cancel out, okay? So we have negative mu k times g equals a. So I can find mu k to be negative a over g. The problem here is that we know what g is, but we don't know what a is. So that's where it comes to find the acceleration. So we have v squared minus v0 squared equals 2a delta x. Okay, initially it will stop. Initially it had a velocity of 1.15 meters per second. So I have 1.15 meters per second squared. 1.15 meters per second squared. 2a delta x is the amount of displacement, which is 0.84. Okay, and the final velocity is 0. Okay, so I have, if I want to solve this for a is negative 1.15 squared over 2 times 0.84. Okay, so a is, if I put that on the calculator, then I would have this number, negative 0.787. So negative 0.787 meters per second squared. Now, once you have that, you can easily get this calculated and put it right there. Okay, so the mu k then is negative 0.787 over g, which is 9.81. So whatever it is, this would be your mu k. Let's take a look at this problem. Our next problem. Go ahead and pause the video, read the problem carefully, write down the things that you have, and then let's come back here and solve it together. So we have sea lion slides from the rest with constant acceleration down a 3-meter long ramp into a pool of water. So this is 3 meters. If the ramp is inclined at an angle of 23 degrees, so this angle is 23, and this ramp is 3 meters long above the horizontal, and the coefficient of kinetic friction between the sea lion and the ramp is 0.26. So mu k is 0.26. Delta x on the ramp is 3 meters. And what else did we have? Theta, it was 23 degrees. Okay, above the horizontal, and the coefficient is that. How much time does it take for the sea lion to make a splash in the pool? In other words, once it starts from right there, the top initial point of 0.0 or 0.1, how much time will it take to hit the ground? Okay, so now we know that along the y direction, all I have, we actually have that. It's not bad, it's good. So this is 23 degrees. This is the sea lion. Okay. And then this is mg. This is n. Now, do we have any other force? No. So if that's the case, I can set up my coordinate system like this. I can come here and set up my coordinate system. Let's choose this color, right? To be along x direction being this, and along y direction being this. So that's x, and that is y. So this is x, and this is y. So along the, whichever force that is along the x or y, I am not touching. But if a force, if there exists a force that's neither along the x direction nor along the y direction, I have to break it down to its pieces or to its components. So n is along y, but mg is not. So what I do, I'll just write mg as mg sine 23 along the x direction, and mg cosine 23 along the negative y direction. Forces along the y direction should always cancel out. So I know n is mg cosine of 23. Okay? That's what I know along the y direction. So along the y direction. Okay, what else do we have? Do we have a frictional force? Yes, because we have a f of k right there. Okay, so that's what it is. Along the x direction, I'll just write down what I have. Second law along the y direction. So second law is telling me all the forces along the x direction should be equal to ma along the x direction. So in other words, I have mg sine of 23 degrees minus f of k being equal to m A sub x. So mg sine of 23 degrees minus f of k is mu k dot n. We know that, right? So this f of k is mu k dot n. That's what it is. So mu k, we know what n is here. From here, we know n is mg cosine 23. So mg cosine 23 equals ma, okay? So I can get rid of m from both sides. If I factor out m, I can cancel out m from left and cancel out m from right. What I have here is this now, sine of 23, g sine of 23 minus g mu k cosine of 23 equals a, okay? If you do that, if you put this, everything in the calculator, you will find g is 9.81, sine of 23 degrees, okay? G is 9.81 again. Mu k is 0.26, right? We have it right there. And cosine of 23 degrees, this will be A. And if you do that, then you can find your A as 1.5 meters per second square. So 1.5 meters per second square. That's what it is for A. But is this what we're looking for? No, we're looking for time. So the problem is asking, let's see what the problem is asking. How much time does it take for the sea lion to make a splash in the pool? So in other words, I am looking for time and not the A, but A is one of the requirements. So delta x equals half a t squared plus v0t. We know the v0t is 0 because initially it was starting from rest at top. So delta x is 3 because the whole ramp is 3 meters. Half a is right there, 1.5. Okay, t is squared. And so t is under the square root. 2 times 3 is 6 over 1.5. And then that means 2 seconds of time. Okay, example 6-3, another very important example. Go ahead and pause the video, work on this problem, okay? Write down things that you have, and then we'll come back and solve it together. Okay, so a flatbed truck slowly tilts its bed upward to dispose of a 95 kilogram crate. So the M is 95 kilogram. So let's write down things that I have. So M is 95 kilogram. For small angles of tilt, the crate stays put. But when the tilt angles exceed 23.3, so whatever angle that I have greater or equal to 23.3 degrees, the crate begins to slide. So that is the minimum requirements, 23.3, to have this box sliding down. What is the coefficient of static friction between the bed of the truck and the crate? So let's see. I have a bit like that. Okay, being this is the minimum requirements, and I have a box which is this box, okay, M. Then I have mg being down I have n being up, and I have an angle of theta. Minimum requirement is 23.3. Okay, so what I have here, do we have, let's see. So we're looking for coefficient of a static friction between the bed and the box. So we're looking for mu s. That's what we're looking for. Okay, that's why it's important to write down things like that. Right. So I have a mg sine theta here. I have a mg cosine theta here. And if it's moving, it is moving along the x direction, right? So it is moving along x direction. In other words, this is your f of s, okay? So along the y direction, I will always have mg cosine theta and n being equal, unless we have another force involved. All the forces along the y direction should cancel out. Along the x direction, since the object is not moving, it's about to move, this is the maximum amount of friction. In other words, mg sine theta should be equal to f of s of max. Okay, so mg sine theta should be equal to mu s dot n, and then I know where this n is coming from. That's where I'm going to use it. So mg sine theta equals to mu s dot mg cosine theta. Okay, so this mg and this mg will cancel out. So it doesn't really matter if it's 95 kilogram or if it's like 195 kilogram. Doesn't matter. I have sine theta being equal to mu s cosine theta. Okay, so mu s is sine theta over cosine theta, or just tan of theta. In our case, mu s is tan of 23.3 degrees, okay, which means 0.429. So this is the 0.429 is being the coefficient. It is unitless. It does not have any unit associated with it. Okay, let's take a look at this example. Now I have a couple of them here that I can solve. So let's take a look at all of them. Let's solve this one. This is a much better than compared to this one. They're all the same. Literally, they're the same. So as long as we're following the equilibrium strategy, we would be able to solve any of these problems. Let's take a look at this one. So go ahead and pause the video, read the problem first, write down things that you have, and then let's come back here and solve it together. All right, so now that you're back, to hang a 6.2 kilogram pot of flowers, a gardener used 2 wires. So as you can see, there are 2 wires here. One is, one is like horizontal right there, and the other one is with an angle of theta. All right, one attaches horizontal to the wall, the other is sloping the wall of the angle of theta equals 40 degrees. So we know what the theta is and we know what the m is. So these are the 2 things that we know. M is 6.2 kilograms and theta is 40 degrees up there, right? So I have a pot of flour, kind of like that. And then this being connected to this, so I have 40 degrees up there. I have T1, T2, and W. So I have W, T1, and T2. Okay. So find the tension in each wire. That's what we were looking for. So if it is staying still, stationary, that means that it does not move. And so at this point is the equilibrium. In other words, all the forces along the x direction should cancel out. All the forces along the y direction should cancel out. So along the y direction, let's see what we have for this point. We have T1, we have W, we have T2 sine 40, we have T2 cosine 40. Okay, so they should cancel out. So W, which is mg, should be equal to T2 sine 40. And T1 should be T2 cosine 40. Okay, so these are the two things that I know. The other one, so if you're looking at this, we have two unknowns and two equations. Okay, if you're looking at this top one, for example, I can write it like this: mg equals T2 sine of 40. Okay, so T2, in other words, is mg over sine of 40. Okay, so mg, m is 6.2, g is 9.81, sine of 40 right there, and I can find T2 to be 94.6 newtons. So 94.6 newtons. If I use that T2 and put it right there, so I have also T1 equals T2 cosine of 40, which is 94.6 times cosine of 40. Okay, then I'll get 72.5. 72.5 newtons for T1. Okay, example 6.13. It's a very common physics example. A block of mass M1 slides, right there, slides, on a frictionless table. So the table does not have any type of friction, this table. So it is connected to a string that passes over a pulley and suspended a mass M2 right there. All right. Find A, the acceleration of the masses, and B, the tension of the string. This is the exact same configuration as of the Atwood machine, okay? Because there is no acceleration right there. So in other words, if I want to write it down, we know what direction the object are moving. They're all moving in this direction. So this is the direction of motion. All right, so then I have W1 as being down, N being up, and W2 being down, and T being up. This is not on any type of surface, so that's why there's no normal surface or normal force here. All right, so if I do that, we are looking for acceleration of the masses and the tension of the spring. Okay, so what I have here is that sigma F equals MA, okay, sigma F along the X and Y direction. So sigma F equals MA. Let me lower the size of the pen. Now, I have, let's see what I have. I have W2 or M2G down, okay? And then I have tension forces. These are internal forces that will cancel out, okay? And then I have N up, which is right there, and W1 or M1G down. These two will also cancel out. This is also frictionless, so I don't have any F of K or F of S in the opposite direction. So all the forces that's responsible for this type of motion is W2 or M2G. So I have M2G equals, how many forces does it hang to? M1 plus M2 times A. So A, or the acceleration, is M2 over M1 plus M2 times G. All right? That's what you have over there. And then if you want to find the tension, you have to write the Newton's second law for one of these objects, okay? Or one of these objects. For example, let's write it down for this one. Doesn't matter, you can write it for that one as well. So if I do that for M2, so for M2, I have W2 down, or M2G down. So I am writing sigma F equals MA for M2. W2 or M2G minus T, which is up, equals M2A. Okay, so I have M2G minus T equals M2. I have A right there. A is M2, M1 plus M2, G. Okay, that's what I have there. And then I can find tension based on that. So tension is M2G minus M2 over M1 plus M2 times G. So T is, I can factor out M2G from both. So I have M2G 1 minus M2 M1 plus M2. So then T is M2G. If you find what's inside this parentheses, you have M1 plus M2 in the denominator. You have M1 plus M2 minus M2. So you'll have M2s will cancel out. And then you are left with T equals M2G, M2 and M2 will cancel out. You have M1 and M1 over M2. The Atwood machine is a very famous problem in physics. And we have a lab about Atwood machine as well. It's very good for determining the Earth gravitational acceleration. It's used for that. So I have solved this here in the Chapter 6 problems, or in Chapter 6 examples. So you can go ahead and take a look at that problem. But the difference here is that we have some sort of a number for M1 and M2 versus the point that I was solving the problem based on just M1 and M2 without any numbers for them. If you remember from the Chapter 6 video, I have proved that if you have a system like this for Atwood machine without any friction and without any mass considered for both pulley and a rope, then you can find that the acceleration of the system is M1 minus M2 over M1 plus M2 times G. That's the acceleration of the system. And the tension is 2M1 M2 over M1 plus M2 this also multiplied by g. So this is what we proved in our lecture video. Now, it is important to note that we consider when we were doing this that M1 was greater than M2. So we kind of think that way and then solve the problem. All right, so you can take a look to see which one is which here. For example, M2 is 4.4 and M1 is 3.1. So here, M2 is greater. So just have that in mind that we solved this, we used this, and we derived these equations considered M1 is greater than M2. So in other words, for your problem, M1 and M2 will switch. Okay? So for this problem, M1 and M2 will switch. Okay. So let's take a look at this example, 6-15. A 1,200 kilogram car round a corner of radius r, 45 meters. So as I said, you have to pause the video, write down the things that the problem is giving you. So right now I know for sure that the radius is 45 meters. 5 meters. That's what the radius is. And I know that it is a 1,200 kilogram car. So M is 1,200 kilogram. Okay, and this is R, by the way. It's not. Okay, that's R, and 1,200 kilograms is the mass. And so if the coefficient of the static friction between the tires and the road is mu s 0.82. So mu s is also given. This is from tire and road, okay? And what is the greatest speed the car can have in the corner without being pulled away, or without sliding, in fact, okay? So in our situation here, I have W or mg down. So this is mg. We have a normal force up, always normal to the surface. And then so this is the direction of motion if this guy wants to go. So this is direction of motion if it's a sliding. But then we have F of S, static friction, preventing this to happen. Okay, the maximum speed happens at the point that it is about to slide, but it's not yet. Okay, so it's maximum static friction. In other words, the maximum static friction is your centripetal force. So F of S of max is ma of c, or centripetal acceleration. So mu s times n equals m. Centripetal acceleration is v squared over r. You remember from the chapter video. Okay, so mu s times n is mg equals m v squared over r. So it doesn't matter what type of mass do you have. This mass and this mass will cancel out. So mu s times g is v squared over r. Okay, mu s is 0.82. G is 9.81. V squared is v squared. R is 45 meters. And in order to find the v squared, I have to multiply 45 with 0.82 and 9.81. If you do that, and then you put this under the square root, so if you do that, then you have to put this under the square root as well. Okay. So if you do this, you will find the velocity to be 19 meters per second. 19 meters per second is the total velocity of this object. Now, if the car is tilted, it's a little bit of a different. You might not need even a huge amount of friction. That's why a lot of these roads on the, when it goes to curve or when you want to turn, it's a little bit tilted. The reason is to avoid sliding the cars. So if a roadway is banked at the proper angle, a car can round a corner without any resistance from friction between the tires and the road, as I just said. So find the appropriate banking angle for a 900 kilogram car traveling 20.5 meters per second in a turn of a radius 85 meters. So we know the velocity of the car, obviously, 25.5 meters per second. I say 20.5. So this is 20.5 meters per second. And we have the turn of 85 degrees. So the R is 85 meters, not degrees. It's the distance to the center of the circle. And the M is 900 kilograms. We won't probably need this M, but we'll see. So what are we looking for? We're looking for theta, or angle. That's what we're looking for. So if you're looking at this, what we have here is we have N in that direction, normal to the surface. Surface is tilted, N is tilted. We have W towards the Earth center, okay? So what I can do is to get rid of this N in this way. So I have theta here. I have my car staying right there, okay? So I have N and I have mg. And by the way, this is the same angle. So this is theta as well. Let me actually make the N a little bit bigger just because I want the N to be bigger in size, okay? So this is N. Then what I can do is to properly get rid of N because it's neither along the X nor along the Y direction. So I have N of X here, or N of Y here, and I have N of X towards the center of the ramp, or towards the center of this imaginary circle, and this R is 85 degrees. Okay, this is center. All right, so if I do that, then what I will get is this, that I have, let me change the color, change the style so I can write much easier. Okay, so we know that all the forces along the Y direction should cancel out. So we know N of Y should be equal to mg. And we know what N of Y is. N of Y is just N cosine theta equals to mg. So that's one equation that I have right there. I'm going to put a star around it. Along the Y direction is that. So along the X direction should be the same thing. So along the X direction, sigma F equals ma along the X direction. And we know that along the X direction, the only force is N sub X equals ma a along the x direction, which is centripetal acceleration. So n of x is n sine of theta equals m. A of centripetal acceleration is v squared over r. Okay, so we have n sine theta equals m v squared over r. That's my second equation. I'm going to put double star around it. Okay, are we missing anything? No. So if I do that, then I can divide, let's divide the double star to one star to see what we can get. So we have n sine theta on the left-hand side and cosine theta on the right-hand side. We have mv squared over r, and we have mg. Okay? So n and n will cancel out. Sine over cosine is tan. M and m will cancel out. We have v squared over rg. So theta is tan negative 1 of v squared over rg, which in our case would be tan negative 1 of v squared 20.5 meters squared over r, which is 85. G is 9.81. Everything inside the parentheses. So then if you find theta, put this in your calculator, what you have is 26.7 degrees, right? So end of the examples, or some examples from chapter 6. Stay tuned, okay?